debugging, I don't think so.
Is it for engineering?
But for engineering, it has a lot of applications. For any type of simulation, it also has a lot of applications. So, for different types of model, for modeling like economics or everything from that to how we use water. Okay, how water flows, in the canal, in the river, and stuff like that. Those are all good applications of differential equations. All right. Well, it is time, so we're going to get started. I'm just going to make sure the recorder is on, and it is. So now we can go ahead and get started. All right. First thing first, work on the homework assignment. The assignment was due last week, and I gave you guys, was it one day or until today? I cannot remember. I can always watch my own video again, I suppose. But I'm pretty sure it's due now. So what we'll do is we'll take a look at the homework assignment and figure out how to, solve the problem. Okay, how to write this particular program. So I'm going to basically do what you would have to do for this particular homework assignment. Download the zip file and I'll work from the file from the zip file itself. Okay, so I don't have need for this anymore. So we'll go unzip sort4, which creates a folder sort4, and inside we have main.cpp, and we'll just kind of work with the main.cpp. The first part of the program is exactly the same as before. The last part of the program is a little bit different. I print basically the 4 variables out at the end of this entire program after you do your magic to sort the values of w, x, y, and z. Okay, so what we want to do is to figure out, okay, how are we going to do it here? Okay, remember what I said? You can basically borrow code from the first homework assignment first. Okay, find out who has the maximum, and then swap with the one. Okay, swap the variable that has the maximum with z, because that's where it's supposed to go. So that's the main logic of this program. You can do it in different ways. The way I'm going to do it is to use this particular way. So I'm going to say if w is greater than or equal to x, and w is greater than or equal to y, and w is greater than or equal to z, and put everything in parentheses, then I'll go do this. If that is not the case, okay, if that is not the case, if w is not the maximum, I'm going to check x and see if x is the maximum. So technically speaking, at this point, I know that w is not the maximum, so I don't even need to bother to compare x against w. So y and z are the only two that I need to compare x against. So if x is greater than or equal to y and x is greater than or equal to z at this point, I can then conclude that x is the maximum. If x is not the maximum and w is not the maximum, then it will be either y or z. So here I only have to compare x to z, y to z. If y is greater than or equal to z, then y is the maximum. Otherwise, the last case would be z being the maximum. So in each one of these cases, what I need to do is to say, well, if I can confirm that w is the maximum, and the maximum is supposed to be z, because if I sort it in that order, w, x, y, z, z is supposed to be one that contains the maximum. So in this case, I have to exchange the values of w and z. Yep.
Is else if the same as putting else and then the next line putting if?
It is the same. Yep. This is just a way to write it, but structurally speaking, that's not actually the way it is displayed here. Yep.
So you can have as much else ifs after that as many as you want.
Say again?
So you can have as much else ifs as you want. Like you have else if,
Like
so you can keep going else if as much as you want, pretty much.
That is kind of correct.
Okay.
It's kind of correct, but they're actually not structured this way. The way it is really structured, if I want to use indentation to represent how this is structured, it's more like this.
Yeah, it's the else if after the other if.
Yep.
And
So
then
what?
there's no curly braces between the after else as or if.
Yeah, just hold on a second here. This is line 49. Okay, so 49 to here. So structurally speaking, it is more like this, because after else, we are expecting one single statement. So in this case, we have a conditional statement as the else statement of the first condition. So we will have to do the same thing with all the other else ifs if I were to use the indentation to display the nesting of the program correctly. So here we have line 52, so we'll say 52 to this point shift. So this would be the correct structure of the program. We really don't have a multi-branch conditional statement. What we really have in C and C++ is just if and else. Okay, so the so-called concept of else if is really an illusion. It is not actually real, but it does the same thing. Okay, it does exactly the same thing. It's just that structurally it should be displayed more like this. So that's a good question. All right, so at this point, getting back to the logic here, we know that W has the maximum, but it's supposed to be over at Z. So what we do is we just exchange the value. You can use the note or whatever we have in the exam, that works too. But you can also use whatever we had in the mock exam, which also works. So we have one more level. Oops, here we go. So that's one way to exchange the values of between W and Z. So at this point, I'll just be a little bit lazy. Just dash it here. Copy that the close curly brace with this one. I don't want to copy that. Okay. So in this case, X is the one that is taking the place of Z. So we just do basically the same thing, except we don't use W, we use X instead, and over here we use Y instead of X.
So each time you're checking the value of Z?
Sorry?
Each time you're checking the value of Z?
Each time I have to make sure that the other variable is the maximum. Okay, the way it works is if this condition is met, that means W has to be the maximum. Okay, or one of the maximums. There can be multiple maximums, but in this case, W has to be one of the maximums. And being one of the maximums, it's not supposed to be here. It's supposed to be over at Z. So that's why once this condition is confirmed, I can then exchange the value of W and Z so that it will be at the right place. Okay. If this condition is not true, then we'll fall to the else branch of this conditional statement. And as the else branch of the first conditional statement, there's another conditional statement, and this is the condition. The condition is between X, Y, and Z is X the maximum. If the answer is yes, X is the largest of X, Y, and Z, and we already know that W, it cannot be the maximum. So in that case, we know that X can be considered the maximum and have it to exchange its value with Z. If this is not true, which means W is not the maximum in order to get to the else branch, but once we get to the else branch, if this is also not true, then we know that W and X cannot be the maximum. Then it can only be Y or Z. Yep.
How do you know that X is the second smallest value?
We don't know. We don't care. We just need to know who is the largest and exchange it. This is only the first step. This is only the first step to make sure the largest value is in Z. That's all I care at this point. Okay? Now, I can finish the rest of the program and test it all in one single shot, but that would not be a good approach. So this is where I would I would stop and check and make sure the program does work up to this point. Okay? So I'm going to save the program first, exit, and use G++ to compile and run the program. Okay, so we compile the program first. And I didn't put in all the switches I'm supposed to, so we'll go ahead and do it again. Dash wall, dash pedantic. There we go. Compiler is still not complaining, which is a good sign. So now we give it 4 numbers. Okay, I can give it like 4, 3, 2, 1. It prints 1, 2, 3, 1, 3, 2, 4, which is not sorted, but the code is not supposed to sort all 4 variables. All it is supposed to do is to put the maximum into Z, and that does. Okay, let's try some other combinations. Let's try 3, 4, 2, 1. and 4 is still at the last one, and then we can exchange these two, and 4 is still the last one, and the last one is just 1, 2, 3, 4. Just make sure that that it does not screw up the easiest of all the cases. Okay, so at this point we have a program that works a little bit. Okay, it doesn't deal with the entire sorting process, but it does make sure the largest value is in Z. Okay, so what do we do now? We have 3 variables to deal with, right? Out of the 4, 1 is already at the right place. So we only have W, X, and Y to deal with at this point. What do you think I'm going to do? Exactly. We figure out who is supposed to be exchanging its value with Y, do the exchange, and then we have 2 left, right? So we'll go back to the program and basically do the same thing. I mean, is this an elegant way to do sorting? No. But given the limitation of what we have talked about, not having access to arrays, this is one of the ways to do it. May not be the smartest way. Once I grade your homework assignment, I'll find the smarter ways to do it, but this works too. All right. Well, okay, out of this code, do we have anything that resembles finding the maximum of 3 variables here? Let me turn on the line numbers so that we can look at the line numbers. From line 48 to line 59, don't we have something that looks like we'll find the maximum of 3 variables, except it is finding the maximum of the wrong 3 variables. But the structure looks about right.
Just copy paste.
Yep, we just have to change the names a little bit, okay? So that's what we'll do. So we'll basically copy line 48 to 59 to here. So we'll say 48 to 59, and we say copy. I think copy is just copy, not use it for a long time. Yep, copy works. Okay, and the indentation is also wrong because it is 1 level indented. So if I want my indentation to correctly reflect the level or the nesting of the statements, we'll have to fix it a little bit. So we'll say from line 61, change the shift width first to 2, and then from line 61 to line 52, do a shift to the left. That's what it does. All right. Now we have to do a massive editing because we're dealing with WXY instead of XY and Z. Okay, so what is the quickest way to get this fixed? There's a really quick way to do it. Z is needed no more. It's no longer needed, right? But W was the one that got eliminated in the first place. So all we really need to do is to change all the references to Z to W for the comparisons. Okay. Is that making any sense? Okay. So when we are comparing, we just change this one to W. So what this is doing is to confirm that X is the maximum of WXY. Now once we know X is the maximum, where is it supposed to go to?
X is
It's supposed to go to Y, right? So we just have to change this to Y. Oops. And then we're done with the first case. In the second case, it will be between Y and W. There we go. Because X is already ruled out as the maximum, so we only got Y and W as the remaining choices. If Y is greater than W, then Y is the maximum, but it's already at the right place. So let's go ahead and exchange these 2 positions here to confirm that out of the 2 variables left, W is the maximum in this case. So in here we have to exchange and say, let's exchange the positions of W and Y, exchange their values, and it will work just fine. Now if you look at line 63 and when you look at line 68, it looks like one will work but the other one will not. But exchange is symmetric. So it doesn't really matter how you say it. Are we exchanging the value of Y with X, or are we exchanging the value of X with Y? It does exactly the same thing. So it should still work. The else case here is corresponding to the case when Y is larger than W. Well, Y is supposed to have the largest value, so we don't have a single thing to do, just like with the other one, when Z is the maximum, there's nothing to do. But what about this? What if I do not know about that, and actually put in the code to exchange Y with Y. Would that hurt? I know it is going to hurt performance, but would that be wrong in terms of logic? And the answer is no. Okay, it's not going to wrong in terms of logic. It will actually still be okay. But since we don't need it, we'll just kind of get rid of it here. All right. Now I will go ahead and run this program. Okay, because now it's supposed to take care of the largest two values out of wx, y, z. So y and z should end up with the largest two values, and they should be sorted. Y is the largest, and z is the largest, and y is the second largest. And this would be a good time to test the program. So I'm gonna recompile the program and just run it again against a few test cases. So we'll give it like 4, 3, 2, 1, and now we have 1, 2, 3, 4. Now that just so happens, to be the case because we are exchanging 4 with 1 and we're exchanging 3 with 2. Okay, so by no means is this any confirmation that this algorithm will sort in general. It just so happens in this case it appears to be that case. So we'll go ahead and exchange 3 and 4. Okay, it's still putting 3 as the second last item and 4 as the last item, so it's still working okay. We'll give it the usual 1, 2, 3, 4. It doesn't touch anything, which is good. So I have reasonable confidence that the program is working, so I'll move on to finish the last bit of this program. So the last bit of this program is to take care of w and x. Those are the only two variables that may still be out of place. So we look at this code here, and it looks like, hey, we can just copy these 4 lines here and make it, the last part of this program. So we'll say, okay, let's copy these 4 lines over here, change the shift width to 2, and then, remove the indentation of these 4 lines. And now it's all between w and x. So if w is larger than x, then we'll exchange w and x. That should do it. That's the last step. Okay. So we'll go. Oops. What did I do? Here we go. So we'll go ahead and recompile the program and give it another try. 5, 4, 5, 3, 5, 2, 3, 1. It sorts it to 1, 2, 3, 4. 1, 2, 3, 5. Excuse me. Let's try 1, 3, 2, 4. It sorts it. Let's try 4, 2, 1, 3. Okay. It sorts it. Okay. So at this point, without actually testing it with all the possible cases, I'm fairly confident that this algorithm is now correct. Yep.
Try like 4, 2, 4, 2.
4, 2, 4, 2. Okay. What is 4, 2, 4, 2 supposed to come out as?
2, 2, 4, 4.
It'll be 2, 2, 4, 4. All right. So any other questions? Is this how you guys did it too? Kind of? Okay. Doesn't have to look exactly like this, but it has to accomplish the same thing. Right. Did anyone actually make use of the array of pointers to integers? No one. Okay. Did anyone try? Okay, well that's okay. I mean, that's not, that really is something that is a little bit ahead of us. So we'll talk about that stuff later. All right, so that's the homework assignment. And this is where we are at this point. We are now going back to talk about input and output using files. We have just talked about how to use printf and cout. Okay, that's where we stopped when we had the midterm. So now we're going to come back and say, but what about inputting? What about being able to read from the input and say, oh, this is a number, that is a number. I think we might have started with that one. Did we start at all? No? Okay. So what we want to do is to start with getting input from a file using scanf, which is actually the slightly more difficult version of the two. Okay. So the note goes like this. Scanf is the counterpart of printf. So printf stands for print formatted. Scanf is basically scan formatted. So it will take the input, whatever you type or coming from a file, it will take it from standard in. Okay, scanf can only take something from standard in. Printf can only print to standard out. Okay, so scanf will basically scan whatever is coming in, and it will interpret whatever is coming in according to your formatting specification and interpret the input accordingly. Okay. So we'll go take a look at the program first and then go back and explain what it does. So here's my program. Okay, line 1 is the pound include. So it's including the header file called standardIO.h, which is basically just telling the compiler how to use scanf. But without this line, the compiler does not know how to use scanf, and it will complain when we get to line 6. On line 5, we are declaring a local variable x, which means x can only be used inside the main subroutine, nowhere else. And on line 6, we have a kind of strange while loop here. When you look at this while loop, the condition is kind of involved with nothing in the body. Okay, and well, let's see what it does, right? When we get out of the loop, we basically return 0. So the question is, what is this program going to do? So the key is scanf here. I mean, this is the entire topic of this particular document, is how to use scanf. So scanf in this case is taking 2 parameters. The first parameter we have seen before. Okay, we have seen this one before when we talk about printf. When you supply %d as the format string to printf, it means we are now going to print a integer signed in decimal. Okay, I think I gave you a link to all the formatting formats. But %d is basically a placeholder to say that, okay, we are dealing with an integer in base 10 and it is signed, which means it can hold positive and negative values. But this time we also have something that we have not seen before. This is the first time we encounter the ampersand symbol all by itself as a unary operator. Okay, when ampersand is inside 2 variables, okay, between 2 variables, it means bitwise AND. Okay, it's called a binary operator because it has 2 sides. Okay, it needs 2 numbers to work with binary. To work with bitwise AND. In this case, it's called a unary operator because it doesn't have the other one. Okay, it is just the ampersand symbol, and in this case, variable x. What this really specifies is the address of x. Okay, I have a new slide that I've just made that talks about addresses and the pointers. So we'll go to that one later. When you look at this entire thing, the focus is, okay, what does it do as a whole? What it does is it will read character by character from standard in, the standard input file, and interpret a number in base 10 and as a sign thing. Okay, but the question now is, okay, now we have a number. What do we do with this number that is specified in the standard input file? It will store it in variable x. That's what scanf is going to do. Okay, it will store the value coming in from standard in, which is usually your keyboard, and it will store that number to variable x. And that's why there's an address of operator here, because in C and C++, well, excuse me, I take it back, in regular C, there's no pass by reference. Okay, for those of you who know what is pass by reference, good. For those of you who do not, we'll talk about that later. Now, what is this comparing with 1? What am I actually comparing with 1? What is the expression that I'm comparing with 1? I'm comparing this with 1. That's because scanf as a subroutine is returning a value. Okay, it's a function. It returns a value. But what is it returning? What is the meaning of the return value of scanf? That would be the next natural question. Yep.
So isn't it, if you don't click 1, that means it's going to be, the while loop is going to equal to 1, so it stays in the loop because that's true.
Nope. Well, we have to figure out what scanf is actually returning, right? So that would be the question. What is scanf returning? Well, there are several ways to figure that out. One is to read the notes, which you are supposed to read ahead of me, right? But assuming you do not read ahead of me, and you can read the rest here, or we can go to the man page of scanf. Can I answer your questions, or? No questions? Okay. So the question is, what is scanf returning? Scanf is not returning the value that it has just read. Okay, that is being put into variable x directly. What it is returning is this. Now, this is a resource for those of you who are planning to become, programmers, because you need to understand, how to find the documentation of well-known procedures or C subroutines. Scanf is one of those things. So when you type man scanf, which is the manual of scanf, it will pop up this page. And in this page, it will describe not just scanf, but the entire family of scanf subroutines. So that would include scanf, fscanf, sscanf, vscanf, vscanf, vsscanf, vfscanf, but they're all basically based on the same principle. Okay. So here's our the one that we have used before. It says right here that scanf returns an integer. This int here in the prototype of a C subroutine is telling you the return type of a subroutine. It is returning an integer, but it doesn't tell you what it means. If you want to figure out what it means, then you can look through the description here. And down in the description, versions, and you will see D would appear right here. Matches an optionally signed decimal integer. The next pointer must be a pointer to an integer, which we have. Okay, the address of an integer is quote unquote a pointer to an integer. So, but we want to skip all of this stuff to get to the return value. These functions return the number of input items successfully matched and assigned. How many items did I request in the program that we were talking about? Okay, let's go back to here. How many items did I specify here? I requested one thing, which is a signed integer in base 10. Okay? And scanf, the return value of scanf is telling me how many things that were actually read. So what would be the expected return value with this particular scanf? If I give it ABC, which is not a base 10 number, what will it come back with? A 0, because it doesn't match a decimal number. If I give it 1, 2, 3, and then press the enter key, what do you think it will come back with? It'll be 1, right? Because I requested one single item, which is a base 10 decimal number. Is 1, 2, 3 a base 10? Can it be interpreted as a base 10 signed number?
Yes.
Well, it matches what I'm looking for, and it will return a 1. So that's why this code is checking for a return value of exactly 1. Okay? So what is it doing in this entire part here? So let's look at this entire sub-expression and say, okay, what does it mean when this is true? What does it mean when this is not true? Let's deal with the true part first. What does it mean when I requested a base 10 signed integer and have it read into x, and it read exactly a base 10 signed integer? I think I just answered my own question, right? I just read, when this is true, it means I have just read a base 10 signed integer and store that value into variable x. But this is there's a conjunction here, right? This is not the only condition in the while loop. The second one is x is different from 0. Okay, how do I get to the second part, the right-hand side of a logical conjunction, logical AND? The first part has to be true. But if the first part is true, that means I just read an integer into x, right? So x is no longer uninitialized by the time I get to the highlighted portion. X is now what I have just read from standard input. So now I'm comparing the number that I have just read and say, is it non-zero? Okay, it can be -1 because it's signed. It can be a negative number. Is it 2? I don't care. As long as it is non-zero, this part is true. So as a whole, this condition is basically saying, get me an integer and see if it is 0. Okay, or to be more positive, to see whether it is not 0. Okay, to see if it's non-zero. As long as I keep reading integers that are non-zero, this won't stop. Okay, this loop, because the condition stays true, so this loop will keep going and going until one of two things happen. Either I gave it a non-number, where scanf returns a 0, and the first condition will fail, and the whole thing becomes false. Or I give it a 0, where the second condition will fail, because I'm in the second condition, I'm asking, is it true or false that x is not 0? If x is in fact 0, then x is different from 0 is going to be false. Okay, so that's the expected behavior of this program. And in the loop here, I have nothing to do. Okay, I'm not even processing the numbers. I'm just doing nothing with the number that I have just read. And here's the return statement, which needs to be there for the compiler to be happy. All right. So what we'll do is we'll type in this program and see whether it behaves the way it's supposed to. So we'll go ahead and I just need to find a way to arrange this so we can see both this and that at the same time. Okay. So we'll go ahead and say read non-zero as my program name, and count includes standard io.h int main. If you do not touch type, it is a good idea to learn how to touch type, because it is really quite useful, for people to write programs. All right, so we have the entire program here. We'll go ahead and compile this program with warn all and pedantic. -O to read non-zero, and then the source code file name is just the same thing with .cpp, compiled without a problem. Now we'll go ahead and run the program. Okay. And it's asking me, it's waiting for me to type something. Okay, if I just type ABC, which is not a number, and press the enter key, what do you think should happen now? It will just exit and give me the system prompt back because the program is done. Okay, so let's check. Yep, exactly. Let's run the program again. If I press, let's say 1, 2, 3, and press the enter key, what should happen? Sorry? It'll be in a loop. It will be waiting for me to type something again, right? Because it's waiting for the next number that I will be entering. So 2, 3, okay, 4, 90, and so on. And here comes the trick, okay? But with 0, what should it do now? It should exit, right? Okay, because it will only keep asking me as long as I'm typing non-zeros. Okay, here's the other one that I want you to. Okay, what about 5 minus 5? That should be 0, right? But what is the program going to read on this line? It will encounter the 5 first, right? And it will say, okay, 5 is a good starting point. It is definitely a base 10 number, okay? So I will definitely be able to tell whoever's asking and say this is going to be a base 10 number. Then it will read the minus symbol, the dash, right? And at that point, okay, scanf is going to say, that's not a part of the number, okay? 5 is the entire thing. So in this particular case, it will read 5, okay, and put 5 into x. And then we will go back to the beginning of the loop again, where it will read negative, right? The minus symbol. The minus symbol by itself is not a problem, okay? Because I did specify a %d as the format string, which means I can read negative numbers. So reading the minus sign as all by itself first is not a problem, because it can be followed by digits to specify a negative number. And obviously in this case, that's exactly what happened. Okay, after the minus 5 and the negative symbol, we have a 5, and at that point, and then the line feed character, which is the end of the line. So the compiler is not the compiler. Scanf is actually happy because now it has just read a negative base 10 number, which is what I asked it to do. So it will return a 1, okay, and I compare the 1 to a 1, they match, no problem. And x at that point will be negative 5. Negative 5 does not equal to 0 is true, so it would actually go through the whole process without any problem. Yep.
What if you were to put that in parentheses?
Then it would fail, because the parentheses, it would not recognize a parenthesis as a part of a number.
Could you force it to read an equation?
No, it cannot. It can only read very, very simple numbers. So in this case, 5 minus 5 is not considered 0. It is actually considered two numbers instead of one. Okay? On this line, 5 minus 5, 5 is considered as the first number. Negative 5 is considered the second number. Okay? And they are two completely different numbers. Okay? If I press the 0 key here, or what if I spell out 0? It's going to get out because it is not even a number. If I specify the number 0, it will still get out, but for different reasons. So there are two, they exit because of different reasons. Does everybody understand that part? If I type 0, the first condition will fail, and that's why it will get out of the loop. If I use the digit 0, the second condition will fail, and that's why it's going to exit the loop. So even though they both end up getting out of the loop, the reason is different. So we're doing okay so far with this program, with this code here. You still doing okay? Yep, go ahead.
What if you could you type in the variable x as the second part? Because we know that when we type in the first number or integer, it's going to check to see if it's positive or negative integer. It'll store that into x. So could you put 5x?
No.
X is not 0.
No, when you specify the input from standard in, x is not considered a number.
Even after it gets initialized in your
Okay, I'm not sure where you want to specify x. Are you trying to specify x while the program is running as a part of the input?
Right, so you see how you have 5 minus x?
Uh-huh.
What if you just put 5x?
That won't work. It will read 5 as a number, but when it comes back and try to read x, x is not a number.
But isn't 5 stored into x?
But this x has nothing to do with the variable x in your program. This x is nothing more than just the ASCII code of lowercase x, which cannot be interpreted as the beginning of a base 10 signed number. As a result, it's going to fail the scanf. Scanf will return with a 0 when it's trying to parse x itself and say this is not a number. Okay? In fact, we'll just do it, and you can see that it gets out because x is cannot be interpreted as a number. Okay. Any other questions about this particular program? Yep, go ahead.
So what does %d does again?
Aha! %d is what we call a format string component. So it specifies, it's a placeholder, and it specifies a signed base 10 integer.
Okay.
Yep.
So if you had like percent string, whatever the abbreviation for the string is, and then the same exact code, unless and then if you start putting in like 1, 2, 3, it would always exit out of the loop.
Well, let's not deal with strings just yet. Okay, we don't have the necessary vocabulary yet to understand what a string is in C++. So we'll just deal with numbers and not with strings yet. All right. So the rest of this program, or the rest of this document, just kind of explains this program in more details, which is what I said. Yep, go ahead.
So just to prove myself, if I'm correct, basically %d allocates space so we can input in x.
It basically said it's asking how do we interpret the content of standard in.
Okay, because
And if we interpret something that is actually matches this, store it in here.
yeah.
Use that as a way to specify where to store the value that we are interpreting from standard in.
Because I kind of expanded on the program and typed in printf and then %d hello. If the condition is true, it will go in and print hello. But with the %d, it just gives me a random gibberish number before hello. If we type in like any number there.
Because you do not specify anything. When you do not specify anything, then printf will interpret whatever the quote-unquote second parameter is. Even if you don't specify one, there's always memory where the second parameter is supposed to be located, and it will interpret whatever is there as the second parameter. So that's why it's printing gibberish, because it's just whatever bit sequence is right next to the string, and it will say, oh, okay, I'll use that as the second parameter and use it as an integer to print it out.
Okay, so
Which is a very bad thing to do.
So how can we specify the D? Just made
When
it
you're
equal
printing?
To, yeah.
I thought we dealt with that before. That's how we print it. You have to supply I. Every time you specify a placeholder, you have to specify a parameter after the format string to match that placeholder. So in this case, I have two placeholders. We have %d as a placeholder. This I is matching that particular placeholder. And we have a %x here as a placeholder. And this I is matching that %x as a placeholder.
Oh, okay.
Yeah. All right. So this would be a good time to take a little detour. Okay, so we will come back and talk about cin instead of scanf. But instead of doing that, I'm going to take a detour and start on the topic of pointers, because we just used the ampersand symbol. So it would be nice to kind of at least know what it is, what is an address, what is a pointer, and so on and so forth regarding that topic. So we just had our first contact with what we call a pointer. Yep. Yep, row sheet is right here. Thanks for the reminder. So I'm just going to start a new column for today. Today is the 20th. There we go. Thank you. All right. So pointers is a kind of like a new topic, and a lot of people do not like this topic in C and C++. Okay, because pointers can potentially lead to a lot of confusion. But it all depends on how we use it and how it is explained. So I'm trying my best to make it not ambiguous, but instead be useful. This is also why cisp360 is a prerequisite to cisp310. Assembly language programming requires the understanding of pointers. Okay, so that's why we have this topic. It's a very big piece in C and C++ programming. There's no such concept as a pointer in Java. Okay, so people who have taken Java before may think up to this point this class is like, oh man, that's boring. But with pointers, hopefully it's not going to be as boring anymore. Okay, so when we talk about, before we even talk about pointers, it is important to understand how variables are stored in a computer. Okay, so that's the first part. I can read my own text here, just word by word, but that would be extremely boring to me. Okay, so that's why I'm not going to do it. So instead, I'll just I remember what I'm supposed to do, so I will just say it in a different way. Variables are stored in RAM, okay, random access memory. When a program is, before you run the program can be stored on the CD-ROM, can be on a hard drive, a thumb drive, and stuff like that. But when you run a program that is in execution has to be in RAM, okay? The entire program has to reside in random access memory. Are we okay with that concept? A program that is already installed but you're not running it, it can be on your hard drive, it can be on a CD-ROM, a thumb drive, or something like that. But when you run a program, when the program is running, it has to be in RAM, it has to be in memory. So that means all your variables must be in memory as well. Are we doing okay so far with that concept? Okay? So in memory, how are variables stored in memory? That's the next question. So the first thing we have to do is to understand, when we are just talking about memory of your computer, how is everything organized in memory? That's the next question. Most architectures that we deal with today, they're called byte addressable processors, or byte addressable architectures, whichever way you want to say it. That simply means you can specify exactly which byte out of your entire memory space that you want to access. That's simply byte addressable. What is a byte? How many bits are there to a byte? There are 8 bits to a byte. Very good. Okay. So the processor cannot access anything smaller than 8 bits or 1 byte, which also means it must have a way to distinguish 1 byte from the next. Is that making any sense? Okay. So how do we make the distinction? How does the process say, I want to access this byte in memory instead of that byte in memory? Each byte has an address, okay? So each byte has an address that is unique to itself, so that you can specify, I want to access this byte instead of the other byte. Very good. So an address of a byte in memory is kind of like a street number of a house on the street. It distinguishes a particular house, they call it a parcel, from the next one, and so on. Is that part making any sense? Okay. But there's a distinct difference between the analogy of a street address as opposed to the address of a byte in memory. There are two differences. One has to do with how the numbers are sequenced. When you're dealing with street numbers, are they sequential?
No.
I have not seen any street number that actually is sequential. So if you start with, let's say 3712, okay, the next one is not necessarily to 3713. 3713 is probably across the street on the other side because it's odd even thing, but the next one on the same side of the street is not 2 more than the number either. It is either 4, 8, depending on the neighborhood, right? With computer memory, it is all sequential. Okay, the next byte simply has the address that is 1 more than the address of this byte, and so on. Is that okay? And then each location is 1 byte. So when you're dealing with a 32-bit architecture, that means you have up to 2 to the power of 32 locations in memory. And approximately how big is that number? 2 to the power of 31. 4 billion something. Okay, so you have 4 billion bytes, and each one is addressable by its address. Are we doing okay so far with that concept? Okay. Most of our variables do not fit into a single byte. Now, how do we know that? What about the 32-bit number? How many bytes do you need to store a 32-bit number? 4 bytes. 32 divided by 8, right? Because there are 8 bits to 1 byte, and a 32-bit number would need 32 divided by 8, which is 4 bytes. So now the question is, what is the address of a 32-bit number? Well, some people may say there's no one single address because it takes up 4 bytes, and each byte has its own address. And by the way, which 4 bytes is it going to take up? Can it take up 1 byte over here, 1 byte all the way over there, 1 byte all the way down here, and 1 byte all the way over there? Nope, it's going to take up 4 contiguous bytes. In other words, whenever you have a 32-bit integer, the 4 bytes that you use to store the integer, they must be contiguous. They must be right next to each other, a single block. And in that case, the address of the 32-bit integer refers to the byte that has the lowest address. That becomes the address of the entire 32-bit integer. Are we still doing okay so far with this concept? Okay? All right. So how does the name of a variable relate to the address of a variable? It seems like both are doing the same thing, right? I mean, this is a way for me to find a variable. So what is the difference? Well, in the document here, which I just typed this morning, so I think no one had a chance to read it yet. Okay, how do you refer to houses in your own neighborhood, like on your own street or apartment complex? Huh?
By the unique address.
By the unique address? Okay, so you'll be the minorities.
With the color, people.
But whatever is easy for people to remember, right? Okay. So in my neighborhood, one house was kind of painted in a very bright orange color. So we call that the pumpkin house, okay, because it kind of is a color like a pumpkin. We refer to houses by the owner's name, like John's house, Jean's house, and stuff like that. We can refer to the house, by the condition of the lawn, or the house with a big oak tree and stuff like that, right? But when UPS comes around to deliver, a package, how does UPS identify a house?
By address.
By the address, right? That's exactly the difference. A variable name is friendly to you as a human, as a programmer. Okay, so you can say, oh, this variable is called sum, and it is supposed to store the sum of a bunch of integers. Okay, but to a computer, to the processor, it uses just the address to refer to a variable. By the time execution gets to the processor, it doesn't care about the name or what we call the identifier of a variable. It only cares about the address of a variable. That's all that it needs. That's all that it needs to know. Are we doing okay so far? Between distinguishing the name of a variable versus the address of a variable. Is that okay? Sort of. Okay. So let me just kind of show you where we are at this point. So we are basically down at this point here. How does an address relate to the name of a variable? Okay, so we're referring to UPS. They need to use the street number on the street, as opposed to us, we can use the name of the owner or some other characteristics to refer to a house in the neighborhood on the street. So now the next question is, how do we get the address of a variable from its name? Okay, bad grammar here. The address of operator is what we have just seen before. It's the ampersand. Okay, so when you say ampersand x and x is a variable, we are referring to the address of x. Are we doing okay so far with that operator, the address of something? Yep.
So would that be the RAM place or the hard drive place?
It's always the RAM place. Okay, the address of something is always referring to the address when your program is in execution. A program in execution is also called a process. Right. So now that we know what is the address of something, why do we need it? Okay, so
Get it. So we can get to it.
sorry?
Why do we need an address of something so we can get to it?
So we can get to the variable, right? Okay, but we can get to variables just using its name, right? I mean, with printf, we just say x and then we can print something from x. So let me just go ahead and give you the two pieces of code, and we'll compare these two pieces of code and say, why is it needed for one but not the other one? Because that is the real question. So when we use printf, okay, if I just want to print the value of variable x, which is an integer, in base 10, this is all I need to do. Okay, I don't need the ampersand. In fact, I do not want the ampersand. If I supply the ampersand here, it will print something that is not the content of variable x. But when you use scanf and you want to read a signed decimal number into x, we have to use ampersand. So why do we need one in printf and we don't need? Excuse me, I take it back. Why do we not use the ampersand in printf, but we need it in scanf? That is the question. Yep, go ahead.
It gives the address where to store for scanf.
Yep. What does this refer to?
It's not some space that's already there. It's
It refers to
variable.
it refers to the value of variable x. So we are printing the value of variable x in base 10 in printf in this case. Okay. This one, on the other hand, is specifying the address of x, not the value of x. Okay, I don't care what is the value of x, I just need to know where is the variable x. And that's because when we are using scanf, we are going to change the variable x. We are not reading its current value, we want to change it. And that's why we need to know the address. It's kind of like you're delivering, let's say a refrigerator to an address. Okay, that's what scanf is doing. Okay, so it needs to know where is the address because I need to go there in order to, in order to finish the delivery. Okay. Are there any questions about why we need to know the address of something in this case? Because the intention of scanf is to alter variable x. In the case of printf, it does not change the value of x. We just need to know what is the value of x. Just give me the value and we are done. Are we kind of doing okay with this Cody, with the difference here?
Mm-hmm.
It's all good? Okay. The difference is kind of like this is looking up, X, like from Street View. This one is actually going to that location. All right. Are we ready to move on a little bit? Okay. So the next question is, instead of just using ampersand, inside scanf, can we store the address of a variable? And the answer is yes, we can actually do that. So there are variables in C and C++ that can store the address of variables. Hold on a second here. This sentence all by itself is kind of cryptic. A variable can store the address of a variable. Doesn't that mean the variable that is storing the address of another variable has its own address, which can be stored in yet another variable? The answer is yes, absolutely. Okay, so that is kind of strange. Okay, that's kind of strange. And these variables collectively are called pointers. Okay, so that's the whole thing about pointers. Pointers are basically just variables that has the address of someone, possibly itself. Okay? That doesn't make any sense to me, right? How can a variable have an address of itself? Now, so instead of using the street address analogy, now I'm going to move on to like one of those mailboxes places, or even with the USPS, you can register and pay up and get a mailbox. So what do you put in mailbox in a USPS, the post office? Just about anything, right? I mean, they have a certain size, not too big. How can you distinguish one mailbox from another mailbox? PO box number, right? There's a number. Okay, so all of these, mailboxes have a number, and you can have, let's say we start with a block of 300. Okay, so 301, 302, 303, 304, 305, 306, 307, and so on. Okay, what can you store in one of these mailboxes? Anything that fits, right? So can I put a little post-it inside, let's say, box 303, and say, oh, you know what? This little post-it is the number of another mailbox, because I'm changing. Okay, I'm changing my PO box from box 303, let's say, to 307. Okay, so I'll just write down here and say, box number 307, and put this little post-it inside this mailbox. So from here on, when someone wants to deliver mail to box 303, that person will say, oh, I'm supposed to put it into box 307, so the actual content will be stored in box 307. Is that making any sense? Okay. Well, in this case, box 303 is a pointer. It stores an address. It stores a way for me to get to another mailbox. That's what a pointer is. Is that okay? If that is okay, why can't I specify 303 here? There's nothing wrong with it, okay? The thing that can be wrong is what you do with it, okay? But there's nothing wrong with using the same number as the box number itself. Yep.
So if you were trying to access that, wouldn't that be like its own loop? Because you're trying to.
It depends on what you mean when you say access it, because accessing is just opening the mailbox and see what is inside. So what is inside here is, oh, I can see that it's a reference to a mailbox. Okay, fine, that's not a problem. It's only a problem when you say, oh, I'm supposed to go there and store something over there.
But it never goes anywhere.
That's okay. It just has a number, 303. It's perfectly okay. It's perfectly okay. Yep.
So using pointers that somehow speeds up the process of the processing itself? Or what's the practical use to it?
Of pointers?
Yes.
Well, the use of pointers, there are many fold, okay? But what we have seen here is the first reason why we need a pointer in this case. Okay, because when we use scanf, we are delivering something to one of the mailboxes. Remember, all variables are inside mailboxes, okay? So when we want to store a value into variable x, we need to know, okay, which box are we talking about? And that's why we need the ampersand here, because I don't care about the content in that box at this point, which is just x itself, okay? When you use x all by itself, you are referring to the content, the current value of the variable. But scanf doesn't care about the current value of x. It wants to know where it is so they can store and overwrite x with a new value. And whenever you need to know where it is, it means it needs an address. And the address of something can only be stored in what we call a pointer type. Are we still doing okay so far with this concept, what a pointer is?
So if you scan a value and you put a pointer x, would the declared x integer above, would that take place of the scan of the item you just put in?
Can you ask that question again?
Okay, like you have the program in the beginning, you have declared variable x. Then you ask to scan for that pointer, and so would that declared variable?
Okay,
be
hold on. We're using scanf to interpret the input in a certain way, and then store the result to where x is. That's what this means. Okay, what scanf does is it will look at the standard input file, read it byte by byte, character by character. It will try to interpret the content of your standard input file using the format string. In this case, it specifies a signed base 10 number. If it does interpret something like that, it will store the result to wherever this parameter specifies. Now, since it specifies the address of x, that means the result will be stored in variable x. It has nothing to do with what is after x or before x. It is just dealing with variable x itself. Yep.
You use the pre and post increment with this. So like, you're looking for the standard input and you're storing it into f or x.
Okay.
The next standard input stores into x++. You do that.
Okay, when you say store into x++, what do you mean exactly?
What do I mean exactly? So I'm incrementing it by 1.
But
so instead of box x,
Uh-huh.
it's box 1 more than x. The next
Aha.
contiguous box.
okay, so you're not talking about incrementing the value of x. You're talking about incrementing the address of x.
Yes.
Okay, there's a way to do it, but it's not ampersand plus plus. It's not ampersand x plus plus. It is a little bit different. Okay, it takes a little bit more to get to that one. Okay. All right. So to answer your question, to use the plus plus operator to get to the next thing, we have to first understand what is a pointer. Okay. So a pointer is basically a variable that stores an address. Okay. So how do we initialize a pointer? That's the next one here. How do we store the address of a variable? So what we do is first of all, we have to declare a pointer first. To declare a pointer, we use the syntax that looks like this. Is int, which is the type of what pint points to. Okay. So the way to interpret the highlighted portion of this slide here is pint points to an integer. The asterisk symbol is point to, okay? But you read it backwards. You say pint points to an integer. Are we doing okay so far? So that makes pint a pointer because it points to something. It points to an integer. But which integer does it point to? We don't know. Okay. Okay, if you just read this part here, we're just declaring that pint is a variable. It points to an integer. But it doesn't say which integer it points to because I have not initialized pint. So at that point, the pointer itself is uninitialized. It can be pointing to anywhere within the 4 billion bytes of your entire address space when you're dealing with a 32-bit architecture. If you're lucky, it points to a location that you're not supposed to read from or write to. And when your program tries to do that, it will just bomb out. Okay, it's called a segmentation fault. If you're unlucky, it points to a location where it can actually change or read from. Then your program will do something bad silently, and it won't show up, the problem won't show up until much later. So that's why pointers are dangerous, because if you are not careful, you can alter memory in your program at places where you're not intending to change, but it won't cause a problem. It will fail silently until you actually make use of the memory content that you have changed like much earlier. Then the problem happens, the symptom would occur. So the time between the changing of a memory location that you're not supposed to the time that you access that location to do something that can cause a symptom to show up can be very long. So by the time your program bombs out, it can be millions and millions of lines from the problem itself. And debugging that type of problem can be very tricky and can also be very frustrating. Okay, so that's why pointers are very, kind of bad in a way, because you have to be careful with these things. So that makes the initialization very important. This is the initialization of pint, which is a pointer to an integer, so that it points to x itself in this case. So what we have here on the right-hand side of the assignment is the address of x. On the left-hand side is the variable pint, and the operation will basically take the address of x, so the pint will now point to variable x. Or the other way to say that is pint will now store the address of x. Having pint storing the address of x is the same thing, exactly the same thing as saying pint points to x. So you can choose one way or the other way to describe what is happening here, but they mean exactly the same thing. In other words, if this is pint, if box 303 is pint and box 307 is x, it means the initialization will basically say I go to box 303 and overwrite the piece of paper in box 303 so that it is now 307. So that when you look at the content of box 303, it says, oh, I am not an integer myself, I am the address of an integer. Box 307 over there has an actual integer. Are we doing okay so far? Now, before you initialize pint, what happens is this piece of paper is still there. Every box has a piece of paper. The question is what is written on that piece of paper. So before you do any type of initialization, this piece of paper can say, well, I know some people do not like this, but I'm going to do it anyway. 666. So it's a piece of paper. It says, go to a certain box, except box 666 is not accessible. So when someone is trying to use box 303 to figure out where to store a value, it will attempt to go to box 666. But since box 666 is not accessible by this particular post office, it will cause a segmentation fault. The program will quote unquote bomb out and say, I can't change that location. It does not belong to me, or I do not have permission to change that location. And so the program will stop execution. Are we doing okay so far with this? More or less? You guys are distracted by the number? I hope not. We can change it. I mean, if you guys don't like that number, we can change it to something. And that number, that box still does not exist here. I mean, if you were a spy, you do not want everybody to have access to your PO box, right? So that's why, that is a privileged location and a normal person cannot get to it. So this is a good time to test all of this stuff, okay? Wait, hold on a second here. If I can use pint to store the location of x, the address of x, doesn't that mean that I can use pint after it is initialized in scanf to take the place of the address of x? It seems to make sense to me, right? If originally I used this syntax and it's okay, the address of x, that means I can store the address of x in a pointer, pint in this case, and then from here on I can just use pint instead of the address of x, because they are the same thing. So as the last thing we do today, we'll go ahead and test this theory and see if it works, because we already have a program that does that, almost everything that we were talking about. So now we go back to this program here, and as we talked about before, I'm going to declare a pointer, pint. And remember, the way you read the declaration of a variable is kind of backwards. So in this case, pint points to an integer. The asterisk symbol means point to, but you read it in a backward way. So now we have to initialize it, right? Because eventually what I want to do is to change this to just pint, not the address of pint. I don't care about box 303. I want to know what box 303 is referring me to. Okay, so that's why pint itself does not have the ampersand in front of it, because it's already the address of something. If I do this, remember what I said? If it's not initialized, it is likely to be the address of a location that I cannot access, and as a result, the program will quote-unquote bomb out having a segmentation fault. Let's test that theory first, okay? And then we'll fix the program and make it work. So we fix the program, and it's complaining about x may be used uninitialized in this function. Okay, but is it a warning? Yep, it is a warning. So as a beginning programmer, I have chosen to ignore the warnings from GCC, as some of you will do. Okay, I'm just gonna say, it's just a warning. I have the executable, I can run the program anyway, I'll just ignore the warning. So let's see what happens when we run this program. It's called a read non-zero. Press the enter key, tag, you were wrong, nothing happens, the program still runs. Well, we haven't reached that part of the program yet. Okay, right now scanf is what we call blocking, which means it is waiting for me to type something. It does not have anything to process, let alone something to store to where pint is pointing to. And that's why the program is not bombing out yet. Okay, if I specify anything other than a number, it's not going to bomb out, because it would just fail and say, this is not a number. I'm not even trying to store anything. So I got to give it something that it will store to a location x, to store to whatever the second parameter specifies. So I can put a 0 here, and then press the enter key, and it gives me a segmentation fault, because pint is pointing to a location where I'm not supposed to be able to overwrite. Is that okay so far? So let's go ahead and use the last 2 minutes of this class to fix this problem, to fix this particular program so that it works. So I go back to the program, and instead of doing this, or in addition to doing this, I now have the initialization and say that pint is now storing the address of x. Or the other way to say that is pint points to x. Okay? With the initialization, the program should work. Okay, so we'll specify like 1, 2. Oh, why is it still crashing?
Wow.
I did not recompile, exactly. All right, so let's go ahead and run it again. This time we will specify the same thing, 12, not a problem. 63, not a problem. 78, not a problem. But somebody may say, oh, Tack, maybe you're just lucky this time. Maybe pint is pointing to some location. It's not x, but it's some location that I'm not supposed to, that I just randomly have access to, because there's a certain range of memory that I do have write access to. So maybe if it is uninitialized, out of the 4 billion something bytes, I just so happen to land on a spot that I have permission to overwrite. Maybe that's the case. But so how do we test this theory that I am just lucky this time? What if I give it a 0? Don't you think that will test whether this program is really overwriting x or not? Because if I give it a 0, what is the second part of the conjunction of the while loop? It checks x, right? It doesn't check what pint is pointing to. It checks x itself. So if I can get out because of a 0, that means it has to be storing to variable x. There's no other explanation why it will work this way. Now, the other way to verify this is to use the debugger, because the debugger can actually let you print out what is pint and what it points to, so you can double check and verify that way too. But this, by itself is also sufficient to show the pint points to x. Yep.
Can you show the source code again?
Sure.
Okay, thank you.
Absolutely. All right. Well, we are running out of time today, so we'll continue the discussion of pointers on Wednesday. Okay, so there'll be a little bit more to pointers, and then we'll move on to something else.